So here's a quick summary of what you should know how to do so far. You know how to use, and this is, I'm talking about double integrals, because otherwise we could go over all kinds of things you know how to do so far in this class if we start from the first day of class with vectors. But I'm talking about double integrals. So one thing we know how to do is we know how to use a double integral to represent area. Area. So like, you know, which is a base of a solid, for example, could be area. And so the way you use a double integral to represent area is you set up your double integral and over the region that you're trying to find the area. And what is the integrand when you're trying to find area?
1.
Mm-hmm. And then you have your area element. And your area element in rectangular could be one of two choices, dy dx or dx dy. And if you're doing area in polar coordinates, then your area element is typically r dr d theta. Usually we don't flip the dr d theta to d theta dr. I'm not going to give you any switch the order of integration problems in polar, thank goodness, because that could get tricky to try to figure out your theta in terms of r. Okay, the second thing that we know how to do with double integrals is you know how to find the volume of a solid. Really? Yeah. And so, for example, if you have a capping surface and it's bounded below by the xy plane, you can use your volume double integral. You do it over your region, which is either the base of the solid in the xy plane, or it may have to be the projection of your solid onto the xy plane if it doesn't isn't flush with your xy plane. And instead of a 1 for your integrand, what do you have here in your integrand?
Function of z.
Function.
Yeah, your capping surface, and then your area element. Now your capping surface might be, if it's bounded above and below by two separate surfaces, you might have to have, instead of just one function there, the taller function minus the shorter function. So you may have that as your integrand, depending on the problem, okay? And then the last thing you know how to do with double integrals now is you know how to find the mass of a planar lamina. And planar lamina is just like a thin film in 2 dimensions. And we just did that last time. And so your M mass is your double integral over the region. And you have some density function, rho of xy. It's just a function of xy. Rho is just some Greek letter, and they typically traditionally use rho to represent density. But you don't have to. If you, I don't like rho of xy, I just want f of xy or g of xy. Okay, fine. That's, if you want to label it that way, that's fine. Okay, I am going to do the derivation now for surface area. So here's what we're going to do right now. Look at this diagram here. You're going to have a capping surface, say there's your surface, and you still have a region of integration down here where it's hovering over, you know, making a shadow, the projection of it there on the xy plane. But instead of finding any volumes, you're going to find the surface area of this capping surface. So if you had to put some gift wrap, you want to know how many square feet of gift wrap you need to cover just the cap here. That's basically what you're being asked to do, is find the surface area of that cap. Now, that's not as easy as it looks. You don't just whip out some gift wrap and go, okay, let's see. Because I don't know how to find area of a surface, you know, unless it's a flat surface. You know, I can find surface area of like a rectangle, a rectangular box by adding up all the surface areas of all the sides of the box. But this thing ain't no box. So the deal is, we're after you get your surface equation here, and there it is, you're going to go, all right, well, I don't know how to find the surface. So what I'm going to do is I'm going to pick a point here in the XY plane, because I've made a huge partition of the region into little itty bitty squares. And you can consider there's n squares. Pick your favorite square down there, you know, your ith square, and look at the area of that little ith square, okay? Delta a sub I, and that just means you're going to have some change of x multiplied by some change of y. And those could be rectangles also, it doesn't matter, rectangles, squares, whatever. Okay, now you're going to pick a point in there, you know, your favorite point inside that little rectangular square, and then see what the corresponding point is up here on your surface. And that point on the surface will have the coordinates x sub I, y sub I, and then it'll have a z sub I, that's your altitude. which can be found simply by plugging your point in the XY plane into the surface function. And that's your Z coordinate. Now, I don't, if I look at the little corresponding curvy surface that's corresponding to all the points in that little rectangle down there, I'm going to call that surface area delta S sub I. Again, I don't know how to find it. I don't know how to find surface area of curvy stuff. I have no clue. And you won't either until we get to the answer. So what I'm going to do is I'm going to approximate. Mathematicians always approximate stuff, but it's a good approximation. And so the plan is, I don't know how to find the area of that curvy thing up there at the top on the surface. So how about instead, I know how to find tangent planes, because we just got done with the chapter on finding tangent planes. And I'm going to make a little teeny itty bitty tangent plane up there that's hovering over the surface. So, sorry. So if you look at this little picture here, right there, keep your eyeballs on that. That's basically what we're doing, is you're taking the curvy kind of greenish surface, which we do not know how to find the surface area of, and we're going to approximate it with the tangent plane instead. And we'll call the surface area of the tangent plane delta T sub I. So that's the plan. We're going to go, hey, that's good enough for government work. If I could find the little area of that little portion of a tangent plane, that's going to be approximately the surface area of the curvy thing. So this is the key right here. So if you do that for every single one of these little rectangles in here, you're going to get like a bunch of little, tangent planes sort of covering this entire surface, and you're going to sum them up. So the sum of all the delta S sub i's, which is what we wish we could get, is going to be approximated by the sum of all the little surface areas of those little tangent planes, which I do know how to find, which you'll see in a moment. Okay, so now we're going to do this kind of in slow motion. And I don't do very many derivations in slow-mo, simply because I don't have time in this course. But I'm going to take the time here just for you, so you can see where this all comes from. Now, the good news is, if you understand what I'm about to do here, and I put any kind of weird problem on the midterm or the final that has to do with this, you will get it. And then further, the benefit to you is when we really get into chapter 17 for reals, and we're going to hit set 17.6 again. This part of 17.6, where we use a double integral to find surface area, we won't have to cover it again. But then we're going to expand and extend that notion of a surface area, and we're going to do, we're going to do flux integrals, yeah, over some surface. Yeah, we're going to find like a, what the vector field is doing is it is, operating there in some region. Yeah, so yeah, it's going to get pretty weird, physics oriented. So pay attention here so you see where this all comes from. So in 3D, if I take my little patch here, this is my patch, my delta T sub I patch, and I blow it up. So I'm going to blow it up. Here it is. Okay, I'm blowing it up. It should look, well, I should probably make it look a little bit more like that. It's going to look like a parallelogram is what it's going to look like, okay? So my little patch, my little T sub I patch is a parallelogram, and I know how to find areas of parallelograms. That's the point. And we're going to use some week 2 knowledge to figure out what's going on here. So this is what I love about this derivation, is because you have to be pretty smart to even understand it. It's pretty cool. I'm going to label the 4 points of my little tiny piece or patch of tangent plane, A, B, C, D. And then here's what I know. If you have 2 vectors that make up adjacent sides of a parallelogram, this is week 2 material. It's going to be on the final, so you better know this. Oh, we're kind of reviewing for the final right now, people. The area of your parallelogram, if you recall this, is the magnitude of the cross product of those 2 vectors that are making up adjacent side lengths for that parallelogram. And this is a key fact that we're going to use in a few moments. So what I'm going to do is I'm going to create 2, sorry about that. I'm going to create two vectors here. I don't know how I got over here. Don't know. So my u and v are going to be the side lengths of this little patch here, of this parallelogram. So how about my u will be the vector AD. So this vector over here is going to be my u. Now, the question is, what are the coordinates of these points? So listen closely. So A, if you look here, the way this patch is, if you drop the patch like down here into the XY plane, you know, projected it, this A is the one that's closest to the origin. So the coordinates for A, I apologize, I don't know why this keeps moving around, has coordinates x sub I, y sub I, and then the z coordinate is f evaluated at x sub I, y sub I, because that point is actually on the surface. And then the point B, which is sort of moving in the direction of the y-axis here, there's B here. So his x will be the same as A's x coordinate, but his y coordinate will be, we're going to call it y subscript I plus 1. So then his corresponding z coordinate is the function f evaluated at his x and y coordinates, which is f evaluated at x sub I, y sub I plus 1. So those are that's the ordered triple for the point B. Okay, now let's do the ordered triple for the point D over here. Okay, his x is, since he's sort of heading in the positive x-axis direction, his x is a little greater than A's original x. So we're going to have his x coordinate be x sub I plus 1. On the other hand, he has the same y coordinate as A because he's not moving in the positive y direction. And so his corresponding z coordinate will be f evaluated at his x and y coordinates, f evaluated x sub I plus 1, x sub I. And then finally, letter C's coordinates, everything has increased. So C has x sub I plus 1, y sub I plus 1, f evaluated at x sub I plus 1, y sub I plus 1. And I know this is very tedious with subscripts and trying to keep track of all this business. And if you're a math major, you should be loving this because you love proofs. If you're an engineer, you're probably bored out of your mind. Okay, so what I'm going to do is form the vectors u, which is going to be AD, and then the other vector I will form will be the vector AB, and I'll call that one V. So here we go, the u, and you guys know that 2 points create a vector, you know, to give it the notation. So, you know, we'll use angular brackets here. We're going to go terminal minus initial 3 times. So for the AB vector, which is also, we'll call it u, you're going to take the difference of the x's, x sub I plus 1, minus x sub I, comma there, sorry, comma, then you'll take the difference of the y coordinates, terminal minus initial, and then you'll take the difference of the or the z coordinates rather. Okay, this is really messy. And this looks pretty gross. You're like, oh my God, this is like horrifying. Don't worry, we're getting somewhere. Now I'm going to do a little bit of rename. So I claim that the difference between x coordinates, delta x sub I, is x sub I plus 1 minus x sub I. Fine. So I'm going to replace this with just simply delta x sub I. Fine. Then what? Well, his second component looks like it's going to get to be 0 because y sub I minus y sub I is 0. And then the last component, which has a big hot mess of the difference of the z's, I'm going to do some replacement here. If I take this delta x sub I formula, which is just the difference of the x's, but I solve it for x sub I plus 1, just for kicks and giggles, and that means add x sub I to both sides, I'll get x sub I plus 1 is equal to delta x sub I plus x sub I, or the reverse, either way, you know. So this f here, I'm going to replace his x sub I plus 1, I'll change colors to make my point, with x sub I plus delta x sub I, like that. And then everything else is going to stay the same, so I'll just go back to my original color, and I got that. Okay, so what? You know, what's the point? And this is sort of the point. we're going to take this last component here and multiply it by a special version of 1. Why are we going to do that? You're going to see in a moment because we're going to clean it up. So what is the special version of 1? I'm going to multiply that last component with. Oh, you're not going to like it. But it's going to be delta x sub I over delta x sub I. Well, why are we doing that? And this is the trick part of the proof, okay? So you're going to go delta x sub I over delta x sub I. And I'm using invisible ink right now. And I'll append a page because I'm going to need a lot more room. Okay, so what of it? Well, like, what's that last component going to go to? So my u is going to end up looking like delta x sub I, 0, and then what I have there, if I take that special version of 1 and just sort of rearrange it a little bit, you hopefully will be able to recognize, sorry, make sure I write this right, what that is. I don't know if you will or not. Let's see who's been paying attention this last month. So one of the delta x sub i's in the denominator, I'm going to move it over, and the other one that was in the numerator, I'll leave it there. Does this look familiar to anybody?
It looks like the limit formula.
Yes, it looks like the definition for a partial derivative, but with respect to what?
X sub I.
Yes, with respect to x. So it turns out what we're going to do is we're going to take a limit as delta x sub I goes to 0, and then we get the first partial. So our u vector is going to look like this. This is pretty cool. And we still have this other delta x sub I like sitting there messing around, doing a bunch of weirdness. Okay, so let's save this for later. Let's save this for later. We're going to need it in a bit. And then we're going to go back to our picture here. And I got to get the other side length of the parallelogram because that's what I was working on. And then I'm eventually going to work up to taking a cross product and then the magnitude of the cross product. You bet. So I need to get the other vector. That's this vector over here, AB, which we're calling V. And so if you do terminal minus initial, terminal minus initial, terminal minus initial for that vector, so V, which is the same as AB, if you take the difference between the x coordinates, terminal minus initial, x sub I minus x sub I, that's 0. And then you take the difference of the y coordinates, y sub I plus 1 minus y sub I, but that's the same as delta y sub I, so we're going to rename it. And then you're going to take the difference of the z coordinates. Okay, fine. Like that. And you're like, oh, now what? Well, just as before, you're going to multiply that last component by a special version of 1, only this time it's going to be delta y sub I over delta y sub I. And you're going to rename this guy after solving this equation here for y sub I plus 1. Y sub I plus 1 is the same as y sub I plus delta y sub I. So what we have right now, if we do the little bit of cleanup, this is what your vector v is looking like. Okay, and so this is where you're supposed to go, oh, yeah, this looks familiar. Oh, my goodness. Yeah, that looks like the limit definition almost, if we take the limit now, of the difference quotient that leads to the partial derivative with respect to y. Woohoo! And that's exactly what's going to happen. So we're going to take the limit as delta y sub I goes to 0. That basically means that you're tightening up your partition down there in the xy plane. And so your other vector v here is looking like 0, delta y sub I, and then the first partial of f with respect to y evaluated at this point, x sub I, y sub I times delta y sub I. Okay, now we're ready for some serious hand-to-hand combat. So we're trying to find the area of the parallelogram. Okay, so what does that mean? And this is where we use knowledge from, 2 months ago. So the area is going to be equal to the magnitude of the cross product. Okay, so we got to go get the cross product first. Oh man, so you're going to go u cross v, and this is where I'm going to dock you for notation. And some of you still haven't listened to me. I don't know if you just don't listen ever to my coaching, but I take away points for bad notation on your handwritten work. I don't care if you get perfect answers on my math lab. If I see yuckiness where you're not even doing these little vector thingies up top, you start dropping in points. So I want to see a 3 by 3 determinant here. In other words, I want to see IJK across the top row. And some of you are like, well, I'm lazy. I don't feel like doing the IJK. Okay, well, congratulations. You're going to drop points. Well, you're just being really strict. Yeah, I am. Thank you. I care about your education. I don't want somebody to look at your paper and go, ooh, where'd you go to school? I want you to walk around proud, you know, chin lifted up, chest up, rib cage up, because you got a good education. And that's good notation. So you're going to put your U components in the second row. So I'm going to run out of the room here. I should probably move this over because my third component's kind of large. You've got that partial multiplied by delta x sub I. And then the v vector, he's got his components in the last row. Okay, he's got the partial with respect to y, fine. And then you do the, you know, the 3 by 3 determinant method. You know the drill. You're going to go, okay, 2 by 2 times I hat minus 2 by 2 j hat plus 2 by 2 k hat. And what you'll notice is, and I'm just going to be a little bit cavalier with the notation. So if you block out, if you block out the row and column that I hat lives in, you're going to get 0 fx delta y, fy delta y. And so the major diagonal is 0, and then you'll get minus, so you're going to get I'll put it in component form, minus the partial with respect to x times delta y, like that. So what? Well, we'll deal with that in a moment. And then your next component. So you block out the row and column that j hat lives in. Okay, so I got delta x sub I. I've got fy delta y sub I. I think I'm forgetting something here. Yeah, this is supposed to be delta x sub I. There should be a delta x sub I in there also. Sorry. And so this guy, block out the row and column, and then I've got this, like this, and then 0. Okay, so you're going to go the product of the major diagonal, which is going to be, and there's a minus there, so don't forget minus these guys, but the minor diagonal is going to give us 0. So this is going to end up being negative, the partial with respect to y, x sub I, y sub I, times delta x sub I, delta y sub I. And then finally, the last guy is with the k hat. So you block out the row and column of k hat, fine. And so what do you get for his little 2 by 2 determinant? You just get the product delta x sub I, delta y sub I. Okay. Now, I want you to notice that the delta x sub I, delta y sub I is a common factor to every single one of these components. And it's like the area element. So if you don't mind, I'm going to factor the delta x sub I, y sub I out because it's a common part of the component. And so what's left here? Now what? We're almost done. Now the area is going to be the magnitude of this, and this is just some scalar that's going to go along for the ride, this area element. So the area of our parallelogram is going to be the magnitude of this cross product, and those negatives are going to get squared, so I'm just going to drop them because I know that when I square a negative, it's going to end up being positive like this. Oops. I'm going to have my commas here. Like that plus, 1 squared, which is just going to be 1. Okay, fine. Now, this is the key. We're getting close. This is my delta A sub I. And then when I take the surface area, and I'm basically going to add up all of these delta T sub I's, which basically look like this. I'm taking the sigma I going from 1 to n of delta T sub I, and that's equal to sigma I going from 1 to n of the square root of 1 plus, your fx, x sub I, y sub I getting squared, and your other partial fy, x sub I, y sub I getting squared, like that, and then your delta A sub I. And then when you take a limit, as the partition tightens up down there, that's those little itty bitty rectangles, and this is what the mathematicians say, take the limit as the norm of your partition goes to 0, and this just means tighten up your partition. You get a double integral. And so what is the double integral that you end up getting? So let's go to the next page, wherever I have, where is it? I think it's on the previous page, sorry. In my notes, it's kind of got pushed to a different page. So that Riemann sum, if you will, there it is, comes up to our definition of surface area here. And I scrolled too far, sorry. Come on, baby. It's right down there. Let's get to it. Okay, so here it is, fill in the blanks. If f and its first partials are continuous on a closed region R in the xy plane, then the area of the surface S, and this is the surface function that you hopefully are given over some region R, is defined as, be careful because some of the notation in me may be different from my math lab just because me and Briggs differ. You're going to have a double integral, but instead of over a region, it's going to be over a surface. You're going to put an S down here instead of an R. So get used to some of this weird notation. And then you're going to put ds. Now ds represents a surface area element. Surface area element. I'm not kidding you, people. And I'm going to use that vocabulary for the rest of the semester. Now, you can't integrate that. It's like, well, what do I do with that? You can't. So you're going to turn it into a regular double integral that you know how to do business with. Well, what's that? Then you turn it into an integral over a region R, which is the projection of your surface onto the xy plane. And then the surface area element is that humongous radical multiplied by dA, where the radical, it has 1 plus fx xy squared plus fy xy squared. Okay, that's the surface area element. And there you have the derivation. Congratulations if you stayed awake for that whole thing. But it's really important that you get this surface area element when we start getting into the physics in chapter 17 and we start doing flux integrals. And if you don't get that we're going to try to find the flux of a vector field over some surface and you don't get this surface area element, you're going to die. Okay, so you'll flunk midterm 4 and you'll probably flunk the final and then you'll flunk the class and you'll take the class again next semester. How fun is that? So don't ask me where that radical came from, because I went over that entire derivation and we did the cross product and we found the magnitude of the cross product of those two vectors, and that's where it ended up having a radical 1 plus fx squared plus fy squared. That's why. So I want you to notice that when you did other mathematics in the last 3 semesters, that would be Calc 1, you do Calc 2, Calc 3, you know that the length on the x-axis, and this is kind of overkill, but let's say, you know, here's the x-axis and you wanted to find the length here between A and B. Well, obviously the length is B minus A, okay? Anybody could see that. But you can actually use an integral to find it, really. I mean, that is overkill. But heck, what if you just integrated 1 going from A to B? That'll give you the antiderivative x, and you evaluate x. Wow, x going from A to B, and you'll just get the length, B minus A. Okay, fine. How about arc length? You did this in Calc 2. Really? Yeah, somebody gave you a function like y equals f of x, and they said, hey, I need you to find the arc length between A and B. This is arc length right here. You know, and you know some other arc length formulas too. They call it little s, and it's the integral going from A to B of the square root of 1 plus f prime of x squared. That's the arc length. And then what about area in the plane? Well, area in the plane is a double integral where you have a 1 as your integrand, and that gives you area in the plane. You can kind of compare it to length on the x-axis. And then finally, we've got surface area in 3D, and that's going to look like a double integral, and this is a surface integral where you integrate over S, and that's going to be that double integral over R with a big old square root where you have 1 plus fx squared plus fy squared dA. Okay, so I'm just going to do a couple of, 3 problems for surface area, and then we're going to get into triple integrals. So today I'm just going to, it's dazzling. A lot of lecture today. Sorry. Gotta catch up. You know, a lot of people are like, oh, well, I just watched the recorded lecture. I hope you do if you're falling asleep right now. You know, I was talking to a colleague last night, not math, and it's a different STEM, particular STEM topic. And this colleague was saying, yeah, I teach synchronously and I don't record any of my lectures. And I was like, wow. And they were just going, yeah, you know, they miss the lecture, they miss everything. I'm not going to, you know, post the notes, I'm not going to record. And I went, interesting, give me some food for thought. All right, so let's do a surface area of a portion of a plane that lies above a circle. So I'm going to draw the picture of the surface area they want us to find, and then we're going to actually find it using this new surface area formula. Well, what's the surface area formula? I just showed it to you. Go back. I just did it. What is it? You know, so when you're taking your quiz Sunday or Monday morning, I know some of you do it last minute, this is something in your notes you better have handy when I ask you a surface area problem. And if I were you, I'd make a little cheat sheet so you have all your formulas ready to go rather than scrambling through lots of your notes and trying to figure out where the heck it is. Or you can read the book because it's all in the book. You're going to do surface area. So how do you do it? So this problem's pretty easy to find the surface area because it's easy to even graph the area. So if you look at the plane and you find the X, Y, and Z intercepts, because I taught you how to sketch portions of planes in space, X-intercept 2, Y-intercept 2, Z-intercept 2. And notice it does say first octant. They don't always say those words, but if they do, that's key. So you're finding the surface area, not of that entire triangle, because then we would just use a formula for area of a triangle. Oh, hell no. We're only finding the surface area of that portion of that triangle I just drew that's hovering over a unit circle. So here's a unit circle. I'll draw a quarter of it here with radius 1 centered at the origin. So this is the region of integration. There's your R right down there. And they're telling you that right there. So if you can imagine the portion of the plane that's hovering over this circle, I claim the surface area they're really asking us to find here, folks, would be this portion right here, that portion of the plane. That's what you're being asked to find the surface area of. Find surface area of that. Kind of looks like a pizza slice, actually. So you might expect that pi might get involved. Actually, it does. Okay, so I claim the surface area is a double integral over the surface ds. That's just your basic generic, but I don't know how to integrate that. So you're going to turn it into a regular double integral that we can do business with. Really, how? Well, this ds is what we call the surface area element, and he's going to get replaced with a big old radical with 3 things inside. 1 plus the partial of f with respect to x squared plus the partial of f with respect to y squared, and then dA. And then you're going to have your double integral symbols there still, but instead of a big old S beneath the 2 integrals, you'll have an R, and that represents the region in the XY plane, which I just drew for you. That's the quarter of a circle in the XY plane. Okay? So you've got your R there. There's your R for us. Now, who's fx and who's fy? Like, what is the function that we're even working with? Because normally you would hope that they give you the surface as an equation z equals f of xy, but I'm lacking that right now. So where is this? That's my question to you.
You just use the plane equation for z?
Yes. You're going to take your plane equation, because that's the surface you're trying to find surface area of, and you solve it for z. And that's not too hard here. If I subtract x and y from both sides of the equation, voila, there's my z, which I can rename f of xy, because they're the same thing. Okay? So it's your plane equation. So how am I going to find the partials of that? Is that hard to do?
No.
Okay, so what's fx?
Now we know. We know.
What? Want to say
So-
something, George?
What's your fx?
Negative
-1.
How about your fy?
-1.
Yeah, oh wow, that's easy. Is that always going to happen? No, but for this problem it did. So you're like, oh my God, this surface area element is just going to be 1 plus, -1 squared, which is just 1, plus -1 squared, which is another 1, and then dA, okay? Now this is just going to be some constant, square root of 3, okay? So my surface area, which they always call big S, is square root of 3 times the double integral over the region. And so there's two ways to finish out this problem, and I'll let you do either way, okay? I'm actually going to let you do the cheesy, sleazy way, so listen up if you like shortcuts. If you like shortcuts, at this point in time, you could go, hey, that's an area. How do I know that's an area, that double integral?
Is it a 1?
Yeah, there's a 1 as the integrand. It's an area of something. Well, what's it the area of? What do you think it represents the area of?
The 3D pizza slice.
No.
Quarter circle.
Yeah, see how it's over R? It represents the quarter of a circle. So Nick, I know you said the whole pizza slice. That would be this entire double integral here that has a square root of 3 involved, which we're trying to find right now. So this right here is the region of integration. The region of integration. That's down here. Okay. So do you guys know how to find the area of a circle? Then you certainly should know how to find the area of a quarter circle without even bothering setting up a double integral. Like, just use your 5th grade math, people. Okay, so 5th grade math. So you're going to go, okay, S is going to be, the square root of 3 is still there, times 1/4 times the area of a circle. And so you're going to go pi r squared. And what's the r for this this circle, quarter of a circle we were doing business with? Anybody see what the radius is?
1.
You're going to go pi r squared, pi times 1 squared, and then you're pretty much done. So your final answer is the surface area is square root of 3 pi fourths square units, because this is surface area. And I'm done with this problem. And that's the easy, cheesy, sleazy way. I did say there's an alternate way. Now, if you were going to do this the hard way, you would go, oh my God, the region of integration is a circle. Shoot, why don't I convert to polar? Which you can. And so then you're going to go, okay, remember the area element, be a pirate. What's dA? drd theta. And what is
Archimedes.
mighty mateys, ahoy, land. And so if you look at your quarter of a circle here, what are the limits for r and theta on this quarter of a circle if you're going to iterate your double integral?
0 to pi halves.
Yeah, 0 to pi halves for the theta. And what about r?
0 to 1.
0 to 1. So you're just going to go, okay, r is going from 0 to 1. You're only going from 0 to pi halves for the theta. And then you can integrate this easy peasy. So you first integrate with respect to r. That's the innermost integral. And you go, oh, come on. That's easy. That's just going to be r squared over 2. Fine. And you'll evaluate r squared over 2 between your limits of 0 and 1. And that's just going to give you a half. And so then you're going to pull the half out. And then you're going to go, okay, I have one more integral left. That's the integral of 1 d theta going from 0 to pi halves. And that's just going to end up having an antiderivative of theta. Fine. And theta is going to get evaluated between the limits of 0 and pi halves. And I hope you can see that you'll have something, but my computer is going nuts. And you'll have square root of 3 halves multiplied by pi halves. And guess what? Guess what? That ends up being the same answer. Questions?
No thanks. good. Yeah.
Okay, so some of you are talking about not recording the lectures. Yeah. You know, I don't know. I think it's pretty hard to learn online. It's nice to have recorded lectures. But the other thing that me and this colleague were talking about was the fact that, and I see it in this class too, and you know who you are. Like a lot of times when I finish class and I go, okay, class is over, bye. Usually, you know, most people leave. Like all of a sudden we're down from 23 people in the room down to like 6. And then the 6 people that are left, I'll go, oh, hi, 6 people. And I'll start calling names of, are you still here? Can I help you with something? And they don't talk. And what does that mean? They're not there. I know you guys are doing that. I know you leave the room.
Oh, wow.
This class does that. All my classes do it, but this class is guilty too. So, you know, if you're just like zooming in and then you go, you know, back to bed, or you go, you know, I don't know what you're doing, and I'll watch it later, you know.
Or they're taking a bathroom break or something.
Consider no. It happens with the same usual suspects. Okay, so let's do a harder problem. This is a harder problem. You're going to find a surface area of a portion of paraboloid that lies above a unit circle. So if I were to graph this one, and you don't have to, but the paraboloid, is z equals 1 plus x squared plus y squared. So it's upward facing paraboloid. You're going to find his surface area, but remember, that's an infinity surface. You're not going to find an entire surface area. Come on. You're only going to find the portion of the surface that exactly hovers over this region in the xy plane bounded by x squared plus y squared equals 1. This right here. So the surface area that you're finding is this underbelly right here. That surface area, it kind of looks like a cup. Okay, so you're finding the surface area of a cup. Fine. So what do we know? We know that S, that's our surface area, is going to be the double integral over the region R, and this down here in the xy plane is our region R, and you're going to have the square root of 1 plus fx getting squared plus fy getting squared, okay? So I claim that this z is the capping surface that we're trying to find surface area of. So what is fx? Quick.
So 1 plus x squared plus y
Careful,
squared.
no,
Or
no,
actually, no, 2x.
I'm just asking for a partial right now, please.
It's
fx,
2x.
what is it? It's 2x, thank you. And what's fy?
2y.
Yeah. So in these blanks over here, I'm going to put these partials. Boom, there we go. Now clean up this radical because it's pretty hellacious. Now, a lot of times you might get these horrific surface integral double integrals that aren't even integrable because, you know, your radical is something, and, you know, you don't want to do trig sub. And it's like, oh my God, forget it. But I'm never going to give you anything like that. I'm going to give you ones that are doable without resorting to trig sub. So don't.
I see what you could do for this one.
Okay, what do you see?
I think if you factor out the 4 and then you convert the x squared plus y squared into r squared, that would help you a lot.
Right. And so what are you doing overall? You're converting this whole thing to?
Polar.
Very good. You are converting the polar right now. And that is an excellent choice, Nick. That's exactly what the heck you want to do for this problem. And the reason why it makes sense is your region of integration is a circle. Anytime it's a circle or a portion of a circle, you're in business. It's going to work out perfectly. So you're going to go, I'm going to have 1 plus 4r squared. And then what does the area element dA end up converting to? Everybody be a pirate.
R.
drd theta, thank you. And then on your region of integration down here in the xy plane, which is just a cute little unit circle centered at the origin, what is the limits, that is, and what are the limits for theta doing on that region?
0 to 2 pi.
Okay, that's for theta, and r?
Would be 0 to 1.
So then you can easily iterate this double integral. Now, is this integral doable? Do you guys know what technique you're going to use to integrate square root of 1 plus 4r squared r dr?
Power
rule.
Power rule, good. And you're going to tell me the u and the du, otherwise you're going to lose lots of points. So who's my u?
1
You
plus
got
4
U
r squared.
r
and
And du?
It's gonna be 8R
8r.
dr.
8r.
Good. So good news, I have an RDR. I just need an 8. I'll put one in, provided I multiply the front by the reciprocal. And then we all know that the square root of u du is going to look like u to the half du. And then the antiderivative of that will be 2/3 u to the 3/2. You need to back substitute your u before evaluating at your limits. I caught some of you on the quiz. You got wrong. I gave you partial credit, but I'm not going to be as nice with partial credit in the future. You better clean up your act. You need to always back substitute when you're doing stuff in this class, and I need to see it. So once you clean up here, you'll still have the outermost integral left. Your antiderivative here is 2/3 u to the 3/2, and then put your u back in, which for us was 1 plus 4r squared, and you want to evaluate that between 0 and 1. So you are going to get a pure number. It's going to be some weird pure number that may not look too cool, but regardless, this 2/3 I'm just going to pull out and then reduce that, so I'll have 1/12. So here I'll have 1 plus 4 times 1 squared to the 3/2 minus 1 plus 4 times 0 squared to the 3/2. And then this whole thing you will integrate with respect to theta eventually. And this is just a weird, I mean, this is horrible. It's like 5 to the 3/2, okay,
I hate this.
minus 1 to the 3/2, which is just 1. I'm just going to pull that out and just leave it. And there's a number, and now it's easy because you're just integrating a 1 with respect to theta, and that's doable because the antiderivative will be theta, and then you'll get this factor of 2 pi. So your final answer is going to be this wacky number, and I'll reduce. Because when you multiply, oh boy, this 5 to the 3/2 minus 1 times 1/12 with 2 pi, you get pi/6. And that's it. That's square units. Ooh, that is some weird number. That's the exact answer. If you punch that up into your calculator, I get approximately 5.33 square units. Okay, that's called surface area. Looking good. Questions?
Thank you.
I'm really seeing the benefits of converting to polar now.
Yeah. Yeah. So this last problem, I'm kind of debating if I even want to do it. I may just set it up just to sort of go over some calculus with you, and then let you deal with the rest of it. And the rest of it's got some algebra involved, so I'll just do. So the picture is they have the portion of the sphere that lies inside a cylinder. So if you draw the cylinder first, so remember cylindrical surfaces, you draw the generating curve, which is x squared plus y squared equals 9, there in the xy plane. And then you whoosh it, whoosh, in the direction of the missing variable, that would be the z-axis. So you get this, can. And that's not the surface area that we're trying to find the surface area. Oh, no, that is not the surface we're trying to find the surface area. What is it? You're trying to find the surface area of the part of the sphere that's inside of this can. Are you kidding me? No, I'm not kidding you. So if you graph a sphere of radius 5, centered at the origin, woo, now that's a sad looking sphere. Bummer. Now, what is the portion of the sphere that lives inside of the can? Well, I claim if I intersect these is you'll have 2 caps. This cap up top and then the cap below. So you end up finding the surface area of the upper, like the north, the North Pole and the South Pole of Earth? That's basically what they're asking you to find, the surface area of the North Pole and the South Pole. Isn't that weird? Now, I'm going to use symmetry, otherwise this is a pain in the butt. So I'm going to claim by symmetry, these 2 areas, surface areas are the same. So my surface area is just going to be twice the area of the North Pole. That's how I'm going to roll. Okay? And that's good enough for me. So they didn't give me a z equals f of xy. So you're going to have to solve for z using your knowledge of, plus or minus and all that good stuff. So your fxy is plus or minus the square root of 25 minus x squared minus y squared. But because we're going to use the upper half of the sphere, the upper hemisphere, we'll take the positive. So in other words, z will be positive, and then we'll also rewrite it in terms of exponents, so it'll be easier to find his partials. So there's your function xy. So now you have it. So your fx is going to be, when you use the chain rule on that baby, and this is why I made you do a lot of chain rule problems. And when you rewrite this in terms of positive exponents and then reduce to lowest terms, and then if you don't have to write using invisible ink, I don't know why this is so slow. Let me see if I can close some stuff down. I don't know. So, nope, that doesn't help. So you can kill off the 2's, and then you have this guy to the half, okay? And you'll do a similar thing with fy. So let me just cut to it. Your fy will be a negative y all over the square root of 25 minus x squared minus y squared. Okay, fine. Then I'm going fast because I'm bored, okay? And I'll show you a fun meme. So my surface area, remember, is going to be a double integral over the region, and that's the region in the xy plane, which is just a circle radius 3. The square root of 1 plus your fx getting squared plus your fy getting squared. So it's going to look like a hot mess, and it's going to look like, oh, I can't integrate this, forget it. And the answer is yes, you can, because you're going to convert to polar, and you'll clean things up by making sure that every the terms in the radicand, you'll combine them into a single quotient. Okay, so I'm not going to do the rest of this, but the idea is rewrite the radicand as one quotient, which is going to take a little bit of know-how and knowledge of algebra, and then convert the whole thing to polar. Yeah, it's going to take some time, but you got to know how to do these kinds of problems. The final answer, believe it or not, is 20 pi square units. So please go try this on your own to see how good you are with polar, because you know on the quiz, I'm going to be giving you a lot of polar stuff, and some of it ain't going to be easy. So try it, okay? So there you have it. There's surface area. Congratulations. Now let's move on to triple integrals. Okay, and here's your mean. I like that mean. And then here's another one. Sorry, nobody's laughing. Oh well.
Oh, that was a good
I
one.
laughed.
I told my dad to look at the memes.
You know, just a little levity here for you, so you can stay awake. Okay.
I hope
I
I
thought they
never
were
run
gonna
into
put
a
like
bear in the wild.
Okay, are you guys still there? You still awake?
Completely.
Yep.
Yeah.
Good. All right. Who's ready for triple integrals?
I think.
Let's do it.
Do it. All right. Who's ready for triple integrals? Woo!
Minecraft bear.
Where are we? 116. Here we go. Triple integrals. It's happening. Okay. I think polar bears are so cute. One of my brothers is really into polar bears. So anytime I get him like a gift or a card, I try to look for something with polar bears on it because he's a big fan.
Yeah, they're
So,
ferocious beasts.
They're pretty bad. Yeah. But when you see them at the zoo and they're like napping and eating carrots or something, you know, they actually feed them carrots. Weird. Then they seem very benign, but you know, you got to know better than that because you don't want to like go into their enclosure and go, "Hey, let's party together, Mr. Bear."
Yeah, they're the
Then it'll rip your lips off.
I believe that they're the biggest bear on the planet per size.
Really? Ooh. Well, you know, maybe if I get a baby polar bear, I could give it a hug. What do you think?
Couple weeks, yeah, sure.
Is the mom near? I don't know.
Oh yeah, wait a minute. Yeah, if the mom's near, I'm gonna be lunch. Yeah,
Begs the
forget it.
question:
Never
can you run
mind.
faster than a polar bear?
I don't know. Probably not. Yeah, well, I'll probably not make it. Okay, so let's do triple integrals. And you know, triple integrals are not that hard if you're okay with double integrals, because we're just going to add an extra layer on there and an extra variable of integration. That's all. So that you're just going to integrate 3 times instead of twice. So what could go wrong, right? As my dad likes to say, if you can't stand the answer, don't ask the question. What could go wrong? Okay, I'm going to do like a penumbra of a proof. All right, fine. So here's the idea of triple integrals. So now instead of a region that's flat in the xy plane, the region of integration is, you guessed it, a solid. So that you can see that sort of green solid. You're going to do a partition and cut that solid into a bunch of little itty bitty rectangular boxes. So that mesh, a bunch of boxes there, is your partition that you're cutting up your solid region Q into. And by the way, some books don't use Q to represent their solid. Some books use a letter E. I think Briggs uses an E. I can't recall. Or a D. Sometimes they call it D. I like Q just because that's how I roll. Okay, but you may see different letters, so don't come up to me and go, oh, I can't do this problem because I like the letter Q too, and they gave me the problem with an E, so I refuse to play the game, and I'm going to go play the game anyway. So you got an inner partition of all these little rectangular boxes, and each of those boxes has a little volume to it, little itty bitty length times a little itty bitty width times a little bitty height. And that's going to be delta x sub I times delta y sub I times delta z sub I. Oh yeah, that's going to be our volume element. And then you tighten your partition. So your norm of your partition, which kind of looks like a magnitude, it's the length of the longest diagonal of one of those little ith boxes. Pick a point in the box and then form this Riemann sum. And then take the limit as the norm of the partition goes to 0. That just means tighten up the partition so your little itty bitty boxes get tinier and tinier and tinier. That's all. And then what do you get? You get a triple integral. Okay, fine. And so what does that look like? Well, you know, it's an integral with 3 symbols instead of 2, you know. So how bad could it be? So you're going to take the limit as the norm of your partition goes to 0 of your Riemann sum, like this, and then your Riemann sum has f x sub I, y sub I, z sub I in it, and you have a delta v sub I, and this turns into a triple integral. So the f x sub I, y sub I, z sub I simply turns into f x, y, z, f of x comma y comma z, times, and then this here is your volume element. And if you're in rectangular coordinates, since it was derived from delta x sub I, delta y sub I, delta z sub I, that's just going to be, you know, dx, dy, dz, although the generic look for it, we'll use the generic look for it for now. The generic volume element is just going to be dv. And then your region of integration is a solid, Q. And this is, of course, provided the limit exists. It has to be integrable. And it might not be if you've got some really bizarre looking surface that isn't integrable on that solid. Okay, now here's the weird part. You remember that the order of integration in rectangular, if you're doing a double integral, is what? Dy dx or dx dy. You have 2 choices. This is for a double integral. How many choices or orders of integration are you going to have for your volume element now, knowing that dv could be dx, dy, dz? So how many possible combinations of order?
Says 6 on the page.
Good. Yeah, somebody's reading. Fantastic. And what are they? Well, dx, dy, dz is one choice. What are the other orders of integration? Well, you just, you know, do all the possible mixtures. You could have dx, dz, dy, or dy, dx, dz, or dy, dz, dx, or dz, dx, dy, or my personal favorite, dz, dy, dx. Okay, so out of these 6, and I'm not going to ask you to switch the order of integration in my class. I do know some professors who teach Calc 3 here at Southwestern, just full disclosure, that do ask you and do give you homeworks and quiz problems where you have to switch the order up of integration between any of these 6. And it can be very hard. I'll just tell you that right now. So I'm just going to say, no, you won't have to. You're welcome.
Thank you.
Thanks.
It would make it hard. But my favorite 2 are these 2 here, where Z is the innermost variable of integration. And then the X and Y could either be your choice, dx dy or dy dx, depending on if you have functions of Y or functions of X. Okay. So those 2 are my favorites, where this one is my all-time favorite. I'll put a star by it. If I can get that order, I try to go for that. Now, how do you iterate the integrals? And it looks like my theorem went all fakaka there. It basically is the way you think. If you're given your solid, and if they tell you the range for all of your variables, then that makes it easy. Sometimes you're not that lucky. And so when you're given some generic triple integral where they're just going, okay, over Q, and there's a volume element, you have to iterate it. You have to put the limits on there and choose your order of integration. If I choose my personal favorite, dz, dy, dx, the outermost integral is going to have pure numbers, A and B. The innermost integral could have pure numbers, or it can have variables, but only with respect to the outermost variable of integration. So you be very careful. So in this case, it could have h1x, h2 of x, and then the innermost integrals limits. Remember, it can't match the variable of integration. If we're integrating with respect to z, it could have x's and y's. So how about g1 of x and y, and how about g2 of x and y? Okay, so that would be how you would iterate it. Okay. So what of it? Now, what can you use a triple integral for? A lot of things. Take this class. And we got, a month left. So there's going to be some fun with triple integrals. So one thing you can use a triple integral for, and if you're a thinking student, you might go, why are you telling us we can use a triple integral to represent volume when you already told us you can use a double integral to represent volume? Well, here's full disclosure. Either one is fine. You can use a double integral to represent volume, or if you prefer a triple integral. Well, which one's better? They're pretty much the same, because it ends up, the triple integral, after you integrate with the innermost integral and you look at it, it ends up matching the double integral that would represent volume. So it's the same, and it takes about the same amount of time. And you just have to follow directions. If I ask you in the MyMathLab quiz or exam, set up the triple integral representing the volume of a solid, and you give me a double integral, well, then I'm going to have to take away a lot of your points because you weren't paying attention to the instructions. So make sure you follow directions. So one way is to use a triple integral for volume. And please notice that if you use it for volume, there's a 1 as an integrand if you use a triple integral to represent volume. You can also use a triple integral to represent the mass of a solid, where the density function is going to be this fxyz, which you'll just simply place into your integrand, and then that'll give you the mass of that solid. Cool. So how do you get your limits? No, well, carefully. Okay. So the way you're going to do it is your z, if you're going to have z as your innermost limits, look at the upper and lower capping surface. If you a ceiling and a floor, that's what's going to help you choose your limits for z. And then the projection of that solid onto the xy plane, that's going to give you your r, and then you'll be able to figure out your limits for what x and y is doing. That's pretty much it. So we'll probably have some more time to do some of this, but I do want to do a couple, at least one example of doing a triple integral. But quick, which one of these is not a meaningful triple integral? We're not going to do either A or B, but how can you tell one of those is completely illegal or not meaningful?
B.
Well, you can't look at the limits.
B.
So why is B not okay? That is correct.
The limits include the variable being different integrated.
Well, which integral is the one that's the problem child?
The second integral.
Yeah, the one here. This is not the middle. The inner one is okay because you are integrating with respect to z, and it's okay to have x's and y's on that innermost integral. It's the middle integral that's yucky. the 0 is fine. Of course, it's always okay to have pure numbers on any limits. The z there, you're integrating with respect to y, and you already integrated with respect to z because you do the innermost integral first. You work from the inside to the outside. And so you shouldn't be even seeing the letter z anymore by the time you get to that middle integral. So that z is unacceptable there. Shouldn't even be there. Well, what should it be? Well, I don't know, because that, whoever set it up wasn't thinking. I don't know what the original problem was. So they screwed up. This one is totally okay. Here the variable of integration for the innermost integral is with z. So it's okay to have x's and y's on the limits there. The middle integral is with respect to y. So it's okay to have an x because you haven't integrated with respect to x yet. And so you get to the outermost integral. Okay, so this one's totally okay. Now let's do an example, and then we'll pick this up next time. Please do not play hooky on Friday, because I'm going to cover the rest of rectangular, and we're going to do cylindrical and spherical, and this is where a lot of students choke. And this is where they actually go down 1 or 2 letter grades on not only the midterm, but also the final, because they don't want to listen to the new coordinate systems of cylindrical and spherical for 3 dimensions. And it is tricky. So be here. So let's just do a triple integral that's already been set up for us. So how hard could it be? Aha! Well, it's not that hard, but you do have to know how to integrate. And this one, you have to be careful, because now that we're adding a third integral into the situation, and you're going to integrate that innermost integral first, in this case, it's with respect to x, you're going to hold z and y constant when you integrate with respect to x. So that means any instances of y and z look like a constant. So how do you integrate z divided by y plus 1 with respect to x?
Just x, right? Like,
Yeah.
in addition to that.
Yeah, you're going to write down the z over y plus 1, because that just looks like some constant multiple. And then you'll have x. And x is going to range between his limits of 0 up to square root of 1 minus z squared. And you still have a couple other integrals left. So I'm going to keep putting those up. And then you evaluate this guy at his limits. And I'm just going to get, okay, square root of 1 minus z squared. Okay, next, we're going to do the integral with respect to z. So is this even integrable with respect to z? What do you guys think? You're going to hold y constant.
It's power rule.
Yeah, this is going to be the power rule. The 1 over y plus 1, it's legal if you kind of want to pull it out and put it in front of this integral, because it is considered a constant multiple. So if you use your power rule, and yes, I want to see those u's and du's, otherwise I'm going to dock you huge amounts of points, because that's how I roll now that we're remote. I get even more strict because there's been yuckiness happening. So good news, I do already have a z. I just wish I had a -2, and I'll put a -2 as long as I put a factor of -0.5 in the front. And then you know the drill, the square root of u du is easy to find the integral of, because that's going to be 2/3 u to the 3/2. And then put your u back in, people. So I'll still have the 1 over y plus 1 as a constant multiple. Then I'm going to have 2/3. Then I'm going to have 1 minus z squared to the 3/2 power. And I'm going to evaluate between the limits of 0 and 1. When you plug in the upper limit, I hope you see it goes to 0. Yeah? Then what? Ooh. What happened to, didn't I have a 2 somewhere here? Oh, I forgot my -0.5. Let me put that out here also. Still there. When you plug in the 1, that goes to 0. And then when you plug in a 0, it goes to 1. So you'll have 0 minus 1, and that, yes, it's to the 3/2, but, okay. It's still going to be 0 and 1. And so you'll end up with just -1. So I'll pull that -1 out front. So what do I have out in front? I have -1, I have a -0.5, I have a 2/3. All that mess is still there. And what am I left with? I'm left with one more integral, and I have to integrate with respect to y. Easy peasy. And that's just the log rule. Everybody see that's a log rule? U is y plus 1, du is just dy. Easy peasy. Integral of 1 over u is just ln. And you're going to take your ln and evaluate him between the limits of 0 and 1. You'll get ln2 minus ln1. ln1 is 0. This whole mess, after reducing, I think it goes to positive 1/3. And then you'll have 1/3 times ln2. And there's your final answer for this cute little triple integral. So there you have it. There's your first foray into triple integrals. Congratulations. Thanks for staying. Goodbye.
That was wild. Okay.
Mhm.